here I could write the same diagram in terms of so what we have done, we have extended or generalized the idea of point particles to one-dimensional objects. Particles and fields are replaced by one-dimensional objects, and at the same time we have spread the vertex, zero-dimensional vertex, to some spreaded vertex in the space-time. And this takes care of these lots of difficulties, like these first three theories, they are perfectly renormalizable theory, whereas this quantum gravity theory, if we construct it with an analogy to field theory, this is a non-renormalizable theory. On the other hand, when you construct this kind of a string theory with this approach, this is a super renormalizable theory, no infinities at all, and it's very understandable. Why? Because we have to think about these singularities at r equal to 0. So in the Coulomb, in the electromagnetism, you have Q1, Q2 by r square. In gravity, you have m1, m2 by r square. So when r goes to 0, you have, this leads to singularities. Okay, so you have a singularity at r equal to 0. In all these first three theories, which means the conventional quantum field theory, comprising of electromagnetic field, strong QCD theory, and electrowave theory. Here, when r goes to 0, this is the singularity, but this is because of the electromagnetic Coulomb law of force. And however, here we have Heisenberg uncertainty principle. So delta x, delta b is of the order of h cross. So when in the loop integrals or in these diagrams that we have shown the virtual particles, intermediate particles, any line connecting two vertices is a virtual or intermediate particle. And here for this virtual particle, energies and momentas can go from 0 to infinity. That is the point. So however, and then if delta p goes to infinite, this would imply that delta x goes to 0. So this is the cause of the appearance of infinities in these theories, in these three theories, or the quantum field theory. Now, and how is it removed? Basically, renormalization theory in terms of these radiative correction diagrams, which you have different diagrams for different theories. For QCD theory, you will have different fundamental radiative correction processes, and for electrowave theory, you will have different radiative correction fundamental diagrams. With the help of that, you can construct higher order diagrams. Okay, and then use the perturbation theory, calculate it term by term, and you can get the transition amplitude for a theory. Now, so basically, it is the uncertainty principle of Mr. Heisenberg. Werner Heisenberg comes to our rescue, and you can smear out this singularity caused at r equal to 0 in the Coulomb law of force. This is being smeared out by the uncertainty principle. So therefore, for string theory, we somehow need to modify this. Okay, and for doing this, what we do is, now this is for QFT, and this is now for string theory, Heisenberg uncertainty principle modified. Okay, so let's modify it. So delta x we define as h cross by delta p plus alpha prime delta p divided by h cross. Okay. So we are effectively modifying the uncertainty principle of Mr. Heisenberg, and we do is by introducing this extra term. What is this alpha prime? This will come out to be the Rajai's law of strong interaction physics, and this is related to the string tension. Some books use T, some books use TS, and this is 1/2 ls square or 1/2 l square. And so alpha prime is related to the string tension. So string tension or string tension in terms of alpha prime, and this we will be using back and forth several times, and this is the length square of the string. And so here now what happens, x min is then of the order of 2 into square root of alpha prime, which is 2 or square root of 2 times ls, and this is essentially of the order of 10 to the power minus 33 centimeters. Okay, so now what happens, this would restrict as a result of this, delta x would no longer go to 0 and delta p would no longer go to infinite. So we have a minimum cutoff distance. Okay, that is what we have done. That now, while introducing the one-dimensional objects called strings, okay, we have appropriately modified this, and now, so here delta x or x min, as I call it, this is of the order of the ls, which is of the order of 10 to the power minus 33 centimeter, and then my delta p does not go to infinity. This delta p going to infinity was causing infinities in my QED, QCD and electroweak theories, because then these were blowing up. Of course, fortunately, with the help of the uncertainty principle, we were able to smear out them, so we were able to renormalize our calculations and get finite results. Okay, that was the thing. Whereas we cannot do the analogous thing with the gravity theory. So if I were to construct a quantum theory of gravity just with zero-dimensional particles, then it would not work. This is the conclusion. By working with zero-dimensional, it just in all the appropriate Feynman diagrams for a particular process, you basically replace these vector gauge bosons like the photon, like W plus, W minus, and G0, like gluons, by gravitons. Okay, that is what you do. So that would be your just analogous theory, quantum theory of gravity obtained by that, but with zero-dimensional particles. And that then you will find that when you use your covariant perturbation theory, or even if you calculate the lowest order diagrams in the quantum theory of gravity by working with zero-dimensional particles, then infinities are unavoidable. We cannot get rid of the infinities. there would be no renormalization procedure that would work for this quantum theory of gravity. And the best way out, I'm not claiming, no string theorist would claim that string theory is the final answer, no. Or is the unique theory of quantum theory of gravity, no. There could be alternative approaches to handle this situation, but string theory remains the leading candidate to understand this situation. That is the, so worldwide at the moment it is supposed to be the most leading theory of, or most widely accepted, let me say, widely accepted quantum theory of gravity. And this is to be done in terms of one-dimensional objects. Okay, so this is one thing. I think I can erase all these things and we could go ahead. Now let us try to define our goal. Once we know that we are going to use this approach, we want to master it or understand it as better as possible. So there is a what kind of generalizations are involved. Okay, we are going to handle in the entire course these following things, like you do classical mechanics or quantum mechanics. You deal with Qi of t, Pi of t, coordinates and momentals. In doing classical mechanics or constructing the corresponding quantum theory, which would be quantum